Welcome to today's paper reading. Today's paper is titled Patchscopes, a unifying framework for inspecting hidden representations of language models. This paper, published in the Proceedings of the 41st International Conference on Machine Learning, introduces a framework called Patchscopes by Asma, Ghandeharioun and colleagues from Google Research and Tel Aviv University. The abstract highlights the importance of understanding the internal representations of large language models, LLMs, to explain their behavior and ensure alignment with human values. The authors propose a novel approach by leveraging the model itself to provide natural language explanations of its internal processes. They introduce a framework called Patchscopes, which is designed to answer various questions about an LLM's computations. This framework unifies previous interpretability methods and addresses their limitations, such as difficulties in inspecting early layers and lack of expressiveness. Additionally, Patchscopes opens new avenues, including using more capable models to explain smaller models and correcting multi-hop reasoning errors. The question of what information is captured in the hidden representations of large language models, LLMs, is crucial for understanding and controlling modern generative AI. This topic has recently attracted significant attention. To address this question, prior work has developed various interpretability methods, primarily relying on three main approaches: training linear classifiers, projecting representations to the model's vocabulary space, and intervening on the computation. However, these methods have practical shortcomings. For instance, probing methods rely on supervised training for predefined classes, which is difficult to scale. Vocabulary projection accuracy decreases in early layers, and the outputs are often hard to interpret. Additionally, these methods do not provide high-quality natural language explanations. In this work, we introduce Patchscopes, a modular framework that can be configured to query various kinds of information from LLM representations. Patchscopes decodes specific information by patching it into the inference pass on a different prompt, designed to encourage the extraction of that information. This framework mitigates the limitations of prior methods and introduces new possibilities for stronger inspection techniques. Figure 1 illustrates the Patchscope framework, which decodes the hidden representation of the token CO from a source prompt. The process involves using a target prompt with few-shot demonstrations to encourage the large language model, LLM, to explain its internal representation. The steps include running the forward computation on the source prompt, optionally transforming the hidden state, running the forward computation on the target prompt, and patching the target representation of the token ? With the transformed representation. This modular approach allows for the design of various inspection methods by configuring the target prompt, model, and transformation. Table 1 provides a comprehensive overview of various prior inspection methods that can be categorized as Patchscopes. These configurations are highlighted in green, indicating their ability to overcome several limitations of previous methods. Notably, these Patchscopes offer more expressive inspection that is free from the need for training data and demonstrates robustness across different layers. The table categorizes these methods based on their inspection objectives, which include inspecting output distribution, extracting features, and resolving entities. Activation patching is a causal intervention tool, primarily used to study the role of certain activations in a model's computation. It has been widely employed for localizing specific information to specific layers and token positions, as well as for identifying information propagation paths within the model's computation. Additionally, cross-model patching, known as stitching, has been used in non-transformer architectures to analyze representational similarity. Despite some limitations, patching remains a key tool for mechanistic interpretability. Probing classifiers are among the most common methods used in inspecting hidden representations of neural networks. These methods often involve projecting into the vocabulary space or extending to other domains, providing insights into the model's internal workings. Patchscopes is a framework that utilizes the advanced capabilities of large language models, LLMs, to translate the information encoded in their hidden representations into human-like text. This is achieved by patching these hidden representations into different inference passes of the same, or different LLMs. The framework is defined by a quintuplet that includes a target prompt, a target position, a mapping function, a target model, and a target layer. This approach encompasses various prior interpretability methods, such as logit lens and linear shortcuts, which project hidden representations to the output vocabulary space using simple mapping functions. Patchscopes not only unifies these methods but also introduces new capabilities by allowing for more complex and varied patching configurations. In the experiment section, we evaluated our framework on several key tasks. For next token predictions, we found that the token identity method consistently outperformed other baselines, especially in later layers, demonstrating that early layers carry significant prediction information. In attribute extraction, our method showed higher accuracy in 6 out of 12 tasks, highlighting its effectiveness without the need for training. For entity resolution, we observed that contextualization of entity names is spread over early layers, with similarity to reference descriptions increasing and then decreasing. These results collectively demonstrate the utility of our framework across different inspection tasks. Figure 2 illustrates the performance of next token prediction estimation across multiple models using precision at 1 and surprisal metrics. The token identity method, which consistently outperforms other baselines from layer 10 onwards, shows significant improvements in both metrics. This method leverages the model's decoding procedure for inspecting representations of different source prompts, demonstrating that hidden representations in early layers carry prediction information regardless of context. The early layers, 1 to 10, exhibit lower performance, likely due to the input contextualization process, which is expected. This figure highlights the effectiveness of the token identity method in accurately estimating next token predictions from intermediate representations. Table 2 presents the feature extraction accuracy results, comparing the zero-shot feature extraction patch scope to a logistic regression probe. Despite not using any training data, the patch scope demonstrates significantly higher accuracy in 6 out of 12 tasks. Statistical analysis using a pairwise t-test with Bonferroni correction indicates that the differences are highly significant, with p-values less than 1e-5 for the marked tasks. This suggests that the Patchscopes approach, which relies solely on the source representation without its original context, is effective in extracting relevant attributes in many cases. Figure 3 illustrates the Rougeau scores of generated descriptions against descriptions from Wikipedia using Vicuna models. The graph shows that similarity between generated and referenced descriptions increases in the first 5 layers and then gradually decreases. This decrease is attributed to contamination from the placeholder token X remaining in the early layers. Notably, the scores for rare, long-tail entities are significantly lower than those for popular entities, indicating a challenge in resolving rare entities. This analysis highlights the utility of Patchscopes in inspecting the contextualization process in early layers of language models. Table 3 provides a qualitative example illustrating how entity resolution occurs in language models. As we progress through the layers, more tokens from the context are integrated into the current representation. The generation column displays the automatically generated text, while the explanation column offers a manually coded interpretation, specifying the entity the generation refers to and how it relates to the processed tokens. This example uses the model Vicuna, 13b, and the subject Diana, Princess of Wales. Figure 4 illustrates an example of the chain of thought, COT, Patchscope, which is used to fix multi-hop reasoning by intervening on the computation graph and rerouting representations. The example configuration involves setting S to pi1, T to pi2, and adjusting the attention mask such that no token in S has visibility to pi2 and no token in T has visibility to pi1. This setup helps in simplifying the consequent reasoning step and ultimately correcting the final prediction. Multi-hop reasoning remains a significant challenge for language models. Although a model might accurately answer each step individually, it often fails to connect these steps, leading to incorrect predictions. Recent efforts to enhance multi-hop reasoning have involved autoregressive prompting and iterative self-refinement processes. However, the authors propose an alternative approach using Patchscopes, which can improve multi-hop reasoning performance without generating reasoning steps. This method involves surgically operating on the model's representations to reroute intermediate answers, thereby simplifying subsequent reasoning steps and correcting the final prediction. In their experiments, the authors generated 1,104 multi-hop reasoning samples, focusing on cases where the model accurately represented each step independently. The Patchscope method achieved an accuracy of 50%, significantly outperforming the vanilla baseline, 19.57%, and the chain of thought baseline, 35.71%. This application demonstrates the potential of Patchscopes in correcting multi-hop errors and highlights the importance of structural information in query synthesis. The authors introduce Patchscopes, a framework that utilizes the text generation capabilities of large language models, LLMs, to decode information from intermediate representations. This framework enhances existing interpretability methods and demonstrates superior performance compared to traditional approaches like projection and probing. Future research should explore how information propagates through different layers and positions, the effectiveness of few-shot prompts, and the potential for cross-model patching. While the framework has broad applications, the current study is limited to transformer-based models, necessitating further research to validate its effectiveness in other architectures and domains. Thank you for watching.